Hello everyone, so my name is David Rousseau. I'm working here at Creatis, and I want to thank first Pascal Picard for giving all the theoretical background, and I will be using part of it, and so it will be kind of loose in terms of less maybe theoretical material, but maybe more oriented toward some life science applications. So we discussed before the school about this balance in the two talks. When I prepared this slide, I realized there was some typo since the INSA logo has changed 1 year ago, and also I wanted also to thank the funding for the school. And in these times of maybe doubts about the usefulness of Europe in some of our partners and collaborators, I think it's a good time to understand what is the point of having this Europe, of having some funding, of keeping the population aware of what can be used at, and also maybe have some gentleman way of collaborating, so that we can keep on having this kind of exchange, which are very thoughtful from my point of view. I will start with some general thoughts, not end with them, but just start with them, because we are on this second day, and some of the nice ideas that I picked up in the first 2 days. First, why we should be very happy to be together, US people and optics people. I think Emmanuel Bossy gave a very great talk on this, because there is a fundamental physical common background when you are talking about wave. Of course, there is this polarization difference that we didn't really comment in the school, but I think really, if you are thinking of curriculum for students, this is really something that you cannot escape. You cannot be only US or only optics. You have this physical background, which is exactly the same. And also, from the talk by Peter this morning, we've seen some biomedical complementarity in terms of selective absorption and penetration depth, and also in vivo compatibility, which is something very important. And okay, so in a plot like this, resolution as a function of depth penetration, all the images of this morning were somehow here in the microscopy domain. And ultrasound, they are very happy people, because they can collaborate somehow with the people in MRI, but also with the people in optics. So this is another very funny stuff. And so I will not be talking about, so, you know, these people working on MRI, they are very nano sensitivity to some molecular imaging, and they would be happy to have some GRAL here to be talking with histological resolution. Hopefully we live in a period where GRAL exists, but they are not accessible to everyone. So for instance, here you have the synchrotron radiation facility, where you have anti-object with very large penetration depths, where you can compare histological-like resolution with the standard of clinics. But this is quite expensive, also funded by Europe. And when you have access to this, it's maybe for 24 hours, and then you have to do all your experiments. So US people, optics people, it's much easier to collaborate, so let's be happy to work together. So I have some recent work on this, and I can tell you it's very hard work. But now enough good happy thinking. Let's go back to the topic of the course, which is another part of my current interest in research. So I will talk about the speckle that has presented Pascal. So speckle is not something only in optics, but will occur in any coherent imaging domain, like ultrasound, laser, but also if you think in interferometry, synthetic aperture radar, and also if you go to ESRF synchrotron, you have something like X-ray laser, and you can use some speckle light, and you will have this kind of also coherency that you recover, although it's, I have to admit, a very specific source. So at the end of the course, you will know how to measure something different than what has presented Pascal so far, is that we will focus here not on the statistical properties of speckle, but how speckles move when there is an underlying biological activity that vibrates or makes the sample on which the coherent light is reflecting or transmitted, and how this vibration can carry some interesting information on the biological activity underpinning in the sample. So at the end, you will know how to measure this biospeckle activity, how to acquire it at rather low cost, and how to simulate it, and maybe some of the main field of application in life science. Of course, there's a lot of reference. Most of the ones that listed Pascal would be meaningful for this, and I picked up the one that I used mainly for this presentation. The nice book by Goodman here, which is a reference for all the theoretical statistical properties of the speckle. And for dynamic laser speckle application, there is this book which I used a lot for the slide. Also, since I have been working in some agriculture application, there is this nice review by the Polish guys, Dunek, which is interesting. So let's let's start with what I call the biospeckle phenomenon. So the setup is very simple. As present Pascal, we have the laser. We will send maybe focus the light on one point of a living object and observe the reflected speckle field. So if you are on this bottle and that there is not that much vibration around, this is what you get, so the speckle field. But as since your object is living, there will be some fluctuations in this, which carry some information relative to this living object, such as movement of scatterers, changes in impedance, and all this will be seen by the wave as some modification of the wavefront that will be recorded on your CCD camera. So I will always present the system like this, but so you can do this acquisition with a lens or without the lens. If you are without the lens, you will get a probe only on one point, and if you use a lens and you shine your object fully with the laser, then you can have a local measurement of this biospeckle activity. So the information is in the temporal plane, temporal dimension on each pixel if you use a lens, and if you don't use a lens, it's the temporal information through all the CCD camera when as you look for the different frames that you require. Okay, so let's have a look in the literature of the main simple metrics that you can use to measure biospeckle activity. So in the context where you don't use a lens, so you have a global measure on a single point, you can use a simple spatial contrast defined like this, where sigma is the spatial standard deviation of the time average speckle pattern. So imagine that you record all these patterns that is integrated by the CCD camera, and so if the speckle is not moving, then you will get a standard deviation which is non-zero. But if it's moving and integrated by the camera, then somehow what you will acquire will be blurred, and so the sigma will decrease. And we can recall, thanks to Pascal, but also I think Emmanuel told this, that in the case of the fully developed speckle, you have sigma which is equal to the average intensity. And so in the case of non-moving speckle, this would be zero, so you will have no speckle activity, but as your camera is integrated all the photons, your sigma will tend to zero, and you can have a biospeckle activity measured by this index, which will tend to 1. So it's very easy, can be calculated or computed from a single exposure, but you have, as a user, you have the responsibility to fix your integration time, which has to be somehow in the same order of magnitude of your characteristic time of the living process. Okay, so in the case where you have a set of sample frame, it's possible to perform direct application of temporal statistics, and so you find this variant of what I presented before. So instead of doing one integration, then you can instead of having the averaging, which is done by the CCD, you can do it on a set of frames and compute your variance here completely numerically, and you recover in the literature some very similar index of biospeckle activity, which here requires an acquisition of set of frames. I have to say here, and I will comment more on this, that although these spatial and temporal contrasts are velocity dependent, they are not directly measuring a velocity or a flow, but more a direct relative measurement of the speckle fluctuation through time. So let's now move on to other global metrics. So what I've proposed people in the literature is something based on the time history of the speckle pattern. So you imagine that on your CCD you record only one line, and then at each time step you give the plot of this line, and so you will have this kind of matrix here if the speckle is absolutely not moving, while if the speckle is moving, then you have something which is very spuriously moving through time. So a low biospeckle activity, and here a high biospeckle activity. So the width of this time history speckle pattern is equal to the number of images that you acquire, and then from this matrix, then you need to maybe put a number to say that this is low biospeckle activity and this is high. So what did people do to do this? How to quantify, to put some numbers of merits for this low speckle and high speckle activity. So people have proposed some inertia moments on the co-occurrence matrix. So let me just give some insight on this. So what is a co-occurrence matrix? For those of you who would not be familiar to this, you choose a displacement vector, and you will construct a co-occurrence matrix on which you count the number of times in your image for which you have the same for a given displacement, so this displacement for which you have a switch from one gray level to another gray level. So this you can compute for all possible switch from one gray level to another gray level. So for instance, 0 to 0, 0 to 1, or 0 to 255 if you are on an 8-bit camera, for a given displacement in the time history speckle pattern. So let's give an example to be more talk a little bit more. So here, imagine that your measurement is this, and you define this displacement. Then you will build your co-occurrent matrix, counting, for instance, the number of times that you switch from 0 to 0 when you move from this pixel to this pixel. So here, for this, it must be 2. There is one here and another one here. So you do this for all possible switch of gray levels, and this gives you your co-occurrence matrix. So let's come back here. So when you're on a low biospeckle activity, whatever the switch from one gray level to another gray level, if you define this displacement along a line, then you will have on a low biospeckle activity something very close to the diagonal of your matrix, while if you have a lot of movements, then you have something which is much larger. And so this is where people put some inertia moment of this on this binary pattern, or absolute value of the distance from the principal diagonal, and so on. So a lot of variance on this. Okay. So after this, generation. Last, global metrics, and then we'll move to the case where we had the lens, so we will do some proper imaging. So what you find in literature is spatial temporal speckle correlation, where you simply take your frame acquired at time t0 that you centered, and you multiply it by the frame acquired at time t, also centered, and you normalize by the standard deviation. So of course at time t equal to 0 you started with 1, and as time evolves, since the speckle is decorrelating, then you have a measurement on this, and for instance, so you will tend to 0, and for instance here you can measure the typical slope at the origin as a measure of the biospeckle activity. Okay, so now let's add a lens on the camera, so that now we are doing some proper imaging, and how do people do some metrics of this Biospeckle activity. So a first idea is, of course, to do some difference between consecutive frames. So it's interesting because it can be implemented real time, and but of course depends on the equation of the time frame and the time characteristic of the phenomenon you observe. So the example here given from the book I listed in the beginning of the talk, where there is this coin where you put some drying paint, and you acquire it at a frame rate of 30 Hz, so a very high frame rate compared to the length of, so very small time frame rate compared to the duration of the drying process. So that between two consecutive frames, not that much at move, but a little bit. So if you do one speckle image, this is what you got, almost no contrast because you have this liquid which is put on the coin. But as you make the difference between two speckle images, you see some contrast appearing because the drying process is not the same depending on the width of the paint that you have, and if you average over 400 difference of speckle, then you recover some contrast that were absolutely not visible with the single shot, single frame acquisition. Yep.
Why you are using Untold?
Yes, so I guess all this team who published this book and who have been very active mainly in the 90s, but I know they are still publishing on this. Work more from yes, and Argentina. Okay. Okay, so some other spatial metrics. So this was nice if you take the difference between two frames, but so this somehow fixed time scale, which is the time difference between the two scales. What if you have multiple characteristic time in your speckle, in your living process? So this is what you get if you are looking for an in vivo maize seed, where you see that the fluctuation of the speckle in the embryo is not the same time characteristic as the one you have in other parts of the seed, specifically in the starch, maybe because there is much more development here than in this other part at the time of the process, the biomedical process. So the second idea is to include differences between non-consecutive frames. So this is known as the generalized difference, where there is still a difference, but you had another time scale which is L here, so it's not just one, it's L, and then you can average over all possible time difference, and maybe put some weight to have a look at some specific time characteristic of interest. So very significant, maybe in biomedical imaging, where you have some rhythmicity and you want to look at some time of the cardiac cycle and not maybe all through the same, all through the cycle. You want to be maybe synchronized and choose your L value here, so that you are at the maximum level of movement and have the best contrast. Okay, so other spatial metrics, all the metrics that are called global metrics can of course be applied on a local window, sub-window of the image, and of course here you have a trade-off between sensitivity and spatial resolution. So all these are quite classical literature that you can find in the 90s, and people are still developing some metrics on this, mainly looking at some Fourier analysis wavelets, also some other basis of decomposition, of temporal decomposition of the signal, like empirical mode decomposition. And all these are important, of course, in biomedical application, where when you have some priors on the biorhythm, which are in the fluctuation that you expect to analyze. Okay, so you can also improve the optical setup. So there is this heterodyne detection that pointed Pascal by Atlan and Gross. But there is also a way to be maybe more quantitative by doing some what is called multiple exposure time speckle, and I'd like to give some short insight on this. this technique of getting information from the biospeckle was actually popped up in one of the papers by Goodman in '65, and there was a corrected version of this paper in '85, and it's linking somehow, giving some more physical link between the statistics that you can do and the images that I presented to you so far, and the velocity, the actual velocity of the scatters that you are that gives the fluctuation of the speckle. So in this very old literature, it gives this relation between the variance of the spatial intensity and the auto-covariance of the temporal fluctuation in the intensity of a single speckle. And so to come back to the velocity of the scatters, you need to have a model for the distribution of the Doppler shifted scatters. So assuming that all these photons are Doppler shifted and that you have, so there is no static scatterers, all scatterers are moving, and you have a Lorentzian velocity distribution, then you can have some model like this, where it will be possible on a single measurement of this spatial contrast, sigma out of E that I presented so far, to come back to a measurement of velocity. But in real life, especially if you're looking at the skin, you have some static scatters, you have some moving scatters, and so you will be somewhere between a Gaussian distribution and a Lorentzian distribution, and from a single measure of time exposure, it will be difficult to come back to this quantity. So this is why people do multiple time exposure measurements to try to come back and to identify a model like this, and to have a kind of more quantitative measurement of the speed. So by preparing the slide, we had this discussion with my colleague Didier, the organizer of the school, and so I thought it was interesting to have the discussion of how all these metrics are found or exist in acoustic literature, ultrasound literature, since we know that this speckle in fact is the same process also in ultrasound. So the technique presented in this course is also used in US, but maybe with slightly different name. Maybe let me point to when it can be used. So I have a small video that Didier was kind to show me, to give me, and show me for this presentation. So I don't know if I can open it. Okay, so this is a case where typically people of ultrasound would not use at all the technique I'm presenting here. So this is a case where you have layers of static, these are static, static scatterers here, and here you have a vessel or a simulated vessel. I think here it was a physical phantom, where you have some scatterers which are in a flow in this direction. So in this case, what people would do in US is do some block matching and particle imaging velocity technique like it was presented yesterday afternoon, okay? And they would not use the technique I'm presenting. Now if we change the configuration and you go something like this one, which is taken from exactly the same phantom, but on a switch perspective, where the flow is coming in this direction, then you cannot do some block matching or particle imaging velocity, and then you can resort to the kind of maybe less quantitative but still informative techniques that I'm presenting in this course. So, a couple of years ago, Didier and some of his colleagues had a look at this, and so interestingly, they had, although with slightly different names, maybe because of also some difference that I did not all capture by looking at it, but so there was this spatio-temporal filtering approach that is somehow close to the time history speckle matrix that I presented, and so these were kind of nice ideas that also pop up with specific application then links to the ultrasound, and also the speckle flow index, which somehow not that far from the generalized difference that I presented to you. So maybe I said that this joint community maybe should share also more, so that maybe all this literature should be maybe more known by each community. But of course, after this, there is a technical constraint that we discussed on the first day, and the application which make that everyone switch apart afterwards. But on the information processing, there are really a lot of common stuff. Okay, so now let me move to the part which is maybe more linked to some stuff that I have done. I had to work with some people interested in stroke, and I wanted to use this technique, but I had, so when I arrived in Lyon 5 years ago. So I was arriving at the lab, not that much funding, so I had a look, so let's buy this system. So this is one commercial solution that you can find on the market. It's a Sweden company, Perimed. So it's something like 30 kilo euros, and on the right, here is what you can, here is what you have. And so something like 100 images per second, and they provide a snapshot which is real-time difference between two images. So not that much advanced metrics that I presented so far. Of course, if you ask kindly, you can have the raw data and do it yourself, but okay. And so a lot of biomedical application, like for the renal disease or diabetes, where the blood flow is not exactly the same. So if you do an ischemia on the arm and you let the the blood come back, you can identify some maybe pathologically irrigated tissue. And also for stroke, if applied on small animals, then you can have a lot of information on how the blood is not coming correctly in the part which is injured due to the acute stroke. And so I decided not to, I had actually not to deal with this commercial solution, and decided to build it myself. So the optical setup is really the one that is described here, but hopefully you have also this kind of literature now, which is associated a paper and a video where people give some more insight, which is maybe cannot be on a letter or even on supplementary data. And so let's have a look at what is said in this video. So they explain how they built.
This video demonstrates a procedure for putting together a laser speckle contrast imaging, or LSCI, system capable of full field imaging of blood flow in small animals. This is accomplished by first setting up both a camera with an attached lens and a laser source that emits diffuse laser light evenly over the field of view of the camera. The second step of the procedure is to prepare a flow phantom or an animal with a suitable window for imaging the desired tissue. The final step of the procedure is to use software to collect images from your camera and turn them into speckle contrast values, ideally in real time. Ultimately, results can be obtained that show images of relative blood flow through laser speckle contrast imaging.
Hi, I'm Adrian Pontecorvo from the laboratory of Dr. Andrew Dunn in the Biomedical Engineering Department at the University of Texas at Austin. Today, we'll show you a procedure for building your own laser speckle contrast imaging setup. We use this system in our lab to study cerebral blood flow. So let's get started.
Laser speckle contrast imaging, or LSCI, is a simple and powerful technique that is used for full field imaging of blood flow. Diffuse laser light creates a speckle pattern, and the speckle contrast value quantifies variations in the speckle pattern that are related to the flow of red blood cells as they pass through it. To begin building the imaging system, mount a camera with a macro zoom lens to a vertical stage, or you could mount the camera to a surgical operating microscope. Now follow the appropriate directions from our website to download the software that will be used to control the camera. Place any object, in our case a simple business card, into the field of view and adjust the lens until it is in focus. You can run the software in live video mode to make sure your object is in focus. Next, set up a laser diode with a collimation kit and then move it over to your object to illuminate it. Turn down ambient light and adjust laser light so that it is evenly illuminating the entire field of view of the camera. Red laser light was used here to make things easier to see, but near-infrared laser light could also be used and has the additional benefit of penetrating deeper in tissue. If a near-infrared laser is used, make sure that your camera does not have a built-in infrared filter that would block the laser light. With the imaging equipment set up, let's see how to surgically prepare animals for experiments.
This is a surgical preparation. Oh, sorry. This one. Okay.
Window over the tissue of interest. This involves thinning the skull over the desired brain region. Begin by placing the urethane anesthetized animal into a stereotactic holder. Use a dissection microscope to remove the skin and tissue surrounding the skull. Now use a dental drill to thin the skull over the desired region until it is transparent. Depending on the experiment, the thinned skull can either be removed or simply left alone. Next, drill a small hole about 2 mm away from the window. This is done because the experiment later involves using a needle to prick the surface of the brain. Finally, use dental cement to create a well around the desired region and place a drop of oil or silicone gel into the well to improve visibility. With the animal prepared, let's see how to collect data.
Yes, we have a stop on this. We discovered this video after we started some first experiments, and we saw the contrast were not that good, and this is really a very important trick to make this small swimming pool and to add some oil. If not, what we are looking at is the blood or some water that you put in, which is drying, and then your speckle activity is very different. So this is a very important trick if you want to do this.
When collecting data, the camera software is used to acquire images and also calculate speckle contrast values. Place the animal into the field of view of the camera, and with the software in live video mode, adjust either the camera height or lens focus until the desired region is seen. Change the position of the laser diode so that it is illuminating the thin skull region, and adjust the laser power to make sure enough laser light is reaching the camera without saturating it. You should now be able to see clear images of the vasculature. Before you are ready to begin your experiment, select the number of images to acquire and how much averaging to do. Also select regions of interest you may want to monitor more closely.
Okay, well, this is quite standard then. So, very interesting. All the details of this article is really, you can reproduce the experiment by looking at it and reading it and looking at this video. There are even proposals to go to lower cost system. Here the camera was quite a good camera in this experiment. And there are some proposals to use maybe less good quality system like a webcam, where they demonstrated quantitatively that they would have similar experience results on the same setup thanks to this beam splitter here. And also, I like this, maybe in echo to the presentation of Peter this morning. So there are some also people, maybe more from the maker or geek community, like here on the symposium on user interface software and technology, that are rediscovering that the optical mouse of the computer was actually also capable of doing some, what I call global measure of speckle movement. And so this is how it has been built, but now they rediscover this and try to apply it in an innovative way, which is what was not thought before for biomedical application, embedded devices and so on. Okay, so are there any other untold tricks? This is what I'm discussing now, to be the part of my talk before we present some other application. So maybe you did not notice, but in this, so everything is rather low cost. The camera, we said it can be a webcam and so on, but there was a very heavy, very stable table in the video. And so if you have a lot of vibration, what you will be looking at is not only the fluctuation of your biospeckle activity, but all the fluctuation that you have. Also, if you have some convection of air on your sample, then this will be what you'll be looking at. And so, is it possible to somehow compensate for this? Also, Peter stated this. All these techniques are producing a huge amount of data. He was talking maybe more about the microscopies, but here, if you do some long acquisition of frame rate, then can you reduce the cost of your data center, which is also part of the system. So this is what I'm presenting here, and so this will be illustrated on apples and seed. So this is the agronomical part of the talk. So can we compensate some parasite fluctuation? So the type of fluctuation we had in mind here was, is it possible to make a handy camera system? So imagine, maybe not, the CCD camera is somehow rolled, and so you can have some macro deviation like this. So interestingly, so what you can do here, sorry, what you can do here is, so you imagine you have a speckle pattern and it's macroscopically moving because your camera is moving. So we are again in the case where US people can do block matching, so we did block matching in this case to compensate for this. And then if these movements are small enough compared to, in terms of speed and compared to the Biospeckle activity, then you will recover after registration your Biospeckle activity. So really, I don't detail more, it's about doing the correlation in the Fourier domain. And so we do the block matching, not to get the signal, but to remove the unwanted fluctuation that we have here. And so this is an example on a plastic bottle. So if there is no fluctuation, you remain at a normalized cross covariance equal to 1. Okay, so cross covariance between the first frame and the frame at time t. Then if you bring some fluctuations, so it means you take your camera, you move it a little bit, so the movement occurs at this time, then you have a dramatic drop of your cross covariance, but after the block matching you recover something which is more or less flat. And this is an application on an apple, so you have a kind of exponential decay. What's happening before you do the registration and after registration, you almost recover the slope, the time slope, which quantifies your Biospeckle activity. Okay, so let's now address the second point that I was pointing at. Is it possible to reduce the amount of data? So we asked ourselves, is it possible to reduce the bit dynamic that we have? So we built it ourselves, a simulator, very similar to the one that described, that was used, in fact, Pascal Picard. So if you want to simulate speckle, you just need to simulate some phasor in the Fourier domain, and then do the Fourier transformation of this. And depending on the number of phasors that you have, so this was the number of sources that was pointing at Pascal, then you will generate some speckle pattern very similar. So this is simulated data on a 8-bit camera, and here on a 1-bit camera. So with this simulation, so sorry, this is a static speckle, and now if I want to simulate some dynamic process, what I can simply do is, so it's an iterative process where I take the phase at the previous time and I add some phase shift, which is much smaller than 2p, if not it will completely decorrelate. So 2p multiplied by this factor t, which is somehow governing the Biospeckle activity. So if this t is close to 1, then it will be completely decorrelated after just one frame, and if it's small, very small compared to 1, then you will have a very long time to decorrelate. So this is how we can simulate Biospeckle activity based on the same static simulator as presented Pascal. And these are the results that we get for this intercovariance, normal intercovariance as a function of time on a simulated 16-bit camera down to a 1-bit camera. So of course there is not that much difference because everybody starts at 1 and everybody finishes at 0. But if you look at the variance as a function of the time, it's also very, very small. So you can reduce the dynamic from 16-bit to 1-bit with a factor less than 2 on the variance of the measurement. This is possible because all the information is not in the spatial domain, but it's in the temporal domain. So as long as your frame rate is correct, then you don't need that much dynamic on your camera. Maybe I will switch this. I was interested in looking at various wavelengths and asked myself if it was possible to work on a mono CCD instead of a 3 CCD camera, and what was the impact of the Bayer filter. And so in the end, if you have speckle grains which are big enough, the answer is that there is not that much difference. So you can work with a mono CCD camera, make a quantification on 1 bit, and have good results. So these are the two systems that I built it myself for working on seeds here. So the seeds are in this part on the left. Sorry. The seeds are here. There is a cover which is transparent to light, so that humidity can remain at controlled level, but it does not that much impact the biospeckle activity, since we are looking for fluctuation, so it's not a problem. Sorry for this. And this was the typical setup that we use, similar to the paper of Jove that I presented before, and we developed ourselves for our system. So cost effective, not only in terms of material, but also in terms of data produced. Okay, so this is the conclusion for this. Now let's have a look at different life sciences applications. So one first application in the domain of plant sciences is about monitoring the imbibition of seed. So this is a viable seed and a non-viable seed, very difficult to know it. It's due to the state of the embryo that you can have information in X-ray, but very difficult impossible to see from the outside. And so to see if they are viable or non-viable, the usual tests are to put them on a wet blotter and to wait the water to come in, and they will incubate and grow. And after maybe 48 hours, you can measure this change of volume, and you can say if it does not change its volume enough, then it's not viable. So it's a kind of destructive testing, but very long, 48 hours. So here, because we have a sensitivity of a fraction of the wavelength on the modification of the speckle pattern, it's possible to go very low under this duration of 48 hours. So this is the result presented on this curve. So here is biospeckle activity that we get from a viable seed and a non-viable seed. Every measurement are repeated a certain number of times to account for the remaining fluctuation that we have in the room due to convection of air or vibration of the plate, which are not compensated by the registration algorithm that I presented quickly. And you can see that maybe after 1 hour you can already have the answer to your test in terms of viable or non-viable seed. So this is a global measurement without any lens. If you add your lens, you can have cartography of your sample. So this is an apple, and people are interested to know if there is an impact or not, which is somehow degrading the sale quality or the customer the quality from the customer point of view. So here it's very difficult from this gray level view. Also not possible from a single speckle shot, but if you accumulate some multiple frame and compute the metrics that I presented to you, then it's possible to detect that due to an impact there is more activity here, more movement detected by the speckle decorrelation or any other metrics that I presented so far. This was somehow pointed by Stefan about the roughness, the impact of the roughness on the speckle. So you can have it in a static, but also on a dynamic if the object is moving. So this was a very recent paper on the biomedical, in the biomedical domain on dental erosion, so a measurement without any lens, so a global measurement on the teeth, which was submitted to an acid attack, and people were measuring the biospeckle activity, which appeared to be well correlated to the roughness of the surface, as measured by maybe more electron microscopy of very local probes. Okay, so let's come back to this stroke problematic. So what's happening during stroke, which is interesting to be looked at, optics rather than other measurements. So during stroke, so there is an occlusion of a vessel for which has consequences that there is no more blood coming in part of the brain. So this is here seen on an angiography. And so there is no more blood coming in this part of the vascular network. And when things occur luckily for the patient, then after the strokes, you can recover, you can reperfuse and have again blood coming here. And these processes are very difficult to monitor with MRI and CT. You because there are processes that can occur on a time window which may be a couple of hours, from 1 to 6 hours. And also these are processes which are governed also by the characteristic time of the heart of the patient. And so it's very difficult to have access to an MRI or a CT for such a long period, and with the time resolution which is gives some information on the hemodynamic characteristic. So if you look at optical techniques, some of them have been listed by Peter this morning. You could go maybe deeper in the tissue if you go NIRS. We will have some photoacoustic tomography maybe this afternoon. We talked about the OCT. Maybe you can go even with better spatial resolution with the 2-photon microscopy. And if you are also governed by a question of field of view and you want to image the full brain of your maybe rat here, then OCT, so LSCI, so laser speckle contrast imaging, appear as a good compromise between all these techniques. So this is where we applied our the system we built, the cost-effective system we built. So if you remember the movie from the Jove, when people have put the oil, in fact we could see all the vessels. There was no need for speckle stuff already in RGB. There was some contrast, and you can see. So that's true for one if you take only one frame. But if you accumulate more and more frame, then you can get a higher contrast on thanks to coherent imaging than what you can get with incoherent imaging in RGB. And this is what is quantified here on this. So the gray level across a given vessel. And so we computed, we calculated that if we were accumulating something like 150 frames, so it's not at 1000 Hz but at 100 Hz, sorry for this typo. If you are accumulating 150 frames, then you get a higher contrast than what you get with incoherent light. Then from this, we were interested in looking at these blood vessels before ischemia and after ischemia, and we did some smart image processing afterwards. So this is where we have fun somehow. So this is part of a job that has been done with Denis Bujoreanu, now PhD student in Matrices with Hervé Lipgott. So we extracted the blood vessel with some vesselness filter, quantified the skeleton, and then have a kind of a graph approach to have a global metric for the connectivity of these vessels before and after ischemia. Last application, so we're reaching the end. So just a few words on this light sheet fluorescent microscopy. I thought it was worth talking about this. Peter talked a lot about OCT, which is meaningful in ultrasound optic stuff because it's basically echography, but since light goes very fast, you have to have a kind of trick to synchronize. And here also, this technique, in addition to be very promising for bioimaging, has there also some interesting similarity with what people do in ultrasound. So, as Hervé Lipgott presented yesterday, the classical way of doing ultrasound is to do some scanning. So you focus on one part of the sample, and then you listen to what is reflected, and then to another part, and so on. So this is basically what is similar to what is done in confocal imaging. And now, because this has some limitation, first of all, because in light, fluorescence somehow photo damage the sample, then a good trick is to parallelize and to have this light sheet illumination, and this is somehow what people are looking at also in ultrasound to get faster. Then they send some plane wave, and this is also a way to go faster in optics. So when you shine this, light sheet in the sample, then you can have some kind of microscopic resolution, and you don't have this superposition of static scatters, moving scatters, and all the limitation that makes the theoretical model was difficult to invest to have a quantitative measurement of speed. And then you can come back to some nice theoretical measurements, like what people do in what is called fluctuation coherent spectroscopy. So what they do is something like they are looking in their voxel of the light sheet fluorescent microscopy. Some fluorescent particle comes in. This is at a scale where there is not that much scatterers, so it's possible to have a link between the correlation and the diffusion model where you are. So if you are on a Brownian motion, on an anomalous Brownian motion, and so with this, the typical metrics that you use here are very similar to the one I presented for Speckle, but in this case, at this scale, then you can go quantitative and have some very nice information on the viscosity or the number of diffuser in the voxel that you have in your 3D imaging. So somehow same principle, but completely different instrumentation setup, although it also bears some similarity with some ultrasound system. Okay, so I'm about concluding before thanking you. So I presented you the Biospeckle phenomenon, which is a fluctuation of the speckle pattern presented by Pascal. Some typical classical metrics that you find in Biospeckle activity, which shows some similarity in US and optics. How to do it yourself at rather low cost. Some life science applications. I had an advertising stuff, but it seems to be, it's okay. Yeah, so before thanking, advertising stuff. So some postdoc position available if some people are interested in image processing and life application on a broad sense. Also, next European meetings, so we have here in Lyon in September the European Microscopic Congress. So we'll have the presence of Emmanuel, so Betzik will be here, and the Nobel Prize in 2014. And we do some hands-on on image processing with so IC, which is a kind of open source platform for bioimaging developed at Institut Pasteur, and which is somehow taking the continuity of Imagy and Fiji, a very well spread software in biology community. We have a communication on correlative optical computed tomography with synchrotron imaging. And also there is this very nice autumn school, Mifobio, organized by the GDR Microscopie Imagerie du Vivant. So Betzik was there also 2 years ago, 2 days before his Nobel Prize. So we don't know if there will be another Nobel Prize in chemistry or physics there, but we'll be there anyway. And so with some hands-on on registration for light fluorescent microscopy, hands-on on how to deal with synchrotron radiation imaging, and also on image denoising. And so I would like to thank so the collaborators, mainly in Milano, with whom we did all this nice cerebral blood flow monitoring. Also my colleagues in Angers for the work on seed and apple. Well, okay, and thank you for your attention.
Thank you very much for a very nice overview going into biology, and also thank you very much for tying all of the topics together.
I tried to, thank you.
That was very nice. We're a little bit behind schedule, but I think we can take time for comments or questions.
Yes. Regarding the laser, you showed from this movie that there is diode laser plus 550. Can you show the picture?
On which one? On my system?
That one.
This one?
No, before that.
Yep.
A simple question. What do you think, instead of using a diode laser, a red diode laser, a helium laser?
What?
A helium laser. Because the helium laser is single mode and is much more coherent than the diode laser. It has more modes and the power changes, so you need to control that. What is your opinion?
So,
nobody has tried.
Okay, my experience, as you have seen, example on apple, viable seed, detecting vessels or not, is that I haven't done some quantitative use of this technique. It was more about classification, detection, 0 on 1, good or bad, imbibated and not imbibated, and so on. So, so this is one point. My experience is that for doing this, I didn't need that much more temporal coherence, so that laser diode was okay. And also, since we do a lot of differences of images at the frame rate where we consider there is no kind of long dip and intensity fluctuation that was impacted so far the quality of the detection in the end. So this is why also from the laser perspective that I did not really detail, there is not that much money to be put to do a system.
Why they are using 532 nanometers?
In this case, sorry, I can't remember. I picked this to show that even with a less good resolution and sensitivity, you could get similar results. But I can't remember why they use this.
Because they are using multispectral.
Yes, so there is this possibility, but I don't want to
no, because the images has some green.
Yes.
And then some red.
Yes, so I can't remember if they compare the two. So everything is in the, since it's open access also. I'm sorry, I can't go to the.
Can it be because they want to have contrast to the hemoglobin?
Yes, so the selection of the wavelength. Also, if you want to go further, as you explained, infrared laser, you will have a thicker sense or probe on your sample.
Or maybe, I mean, if you look at in the red, you have very little absorption from hemoglobin.
Yep.
So basically, you could enhance blood flow by doing two images and subtracting, basically.
Yeah, there are some tricks like this. I can't remember if they do this. This is not the core of their article. It was more about applying a technique, maybe this one to a dual wavelength and comparing the two CCD.
Yes, please.
Have you experimented on the distribution of speckles on different regions of the application?
Yeah. So I get the last part, but not the first part. How do you what?
Distribution.
Yeah.
Experimented with distribution of speckles. So it could be classification.
Yes. Yes. I have some work in progress on this, but so especially you can use a nice paper by Philippe Réfrégier from the mid 2000, I would say, on the contrast that you have when you have depolarization. So we said that on polarization we have sigma out of E, which is 1, and it's not the case when it's partially polarized. So looking at the first order statistic, then you can have some contrast on depolarization, which we did not really discuss in this school because it's part of the physics which is not in common with acoustics. But so you can have information on this, plus also you can have some contrast on reflectivity or intensity, and so if you have a given scale, then you can do some nice segmentation by so everything is in the good man concerning this contrast that you have in the partially polarized wave. Because then it's, you do an exponential decay plus an exponential decay by random variable, and this gives you a kind of relay law.
Thank you. Are there other questions or comments? If that's not the case, I think we should thank both our speakers of this session. Thank you very much.